Now let's consider continuously switched circuits. So let's first look about how to create a square wave. Nearly all continuously switched circuits, also called clock circuits, are going to be commanded by capacitance and resistance loads. Okay, even in digital circuits, the capacitance and resistance are still going to affect those switched circuits. So let's consider mathematically first our unit step function that we had before. So it's initially 0, and at some time, which we've called 0, it becomes a 1. Okay, so that is the unit step function from before. Here it is on a graph. This is showing how you can produce one side of a square wave. We can combine that idea to create a square wave by subtracting a delayed version of that unit step. This will give us a square pulse that is 0.5 seconds wide for this example. So we say that V of t is equal to the unit step U of t minus U of t minus 0.5. That's the unit step delayed. And this will give us a pulse. If we take the switch and we open it at time 0 and then close it at time 0.5 seconds, and then we open it again and then we close it again, we will end up with a square wave like we have shown here. So now let's consider what happens when we apply this square wave to a circuit. So assume we have a square wave where the input alternates between minus 12 volts and 12 volts, and it switches every 0.5 seconds, every half second. As long as our circuit is linear, then we can scale and add different responses together, just like we've looked at before in this class. Our responses will be delayed in time based on the turning off and on of the switching. If the circuit elements don't change their VI characteristics over time, we say that the circuit is time invariant. And LTI circuits are an important case of systems. Linear time invariant systems are very important in electrical and computer engineering. When we look at this, the downward step response will be the negative going version of the original answer, but it will be delayed by the switching time 1 over 2 times 1 over 2s, half a second. There's one more problem we have to figure out. We don't know what the initial value is for the delayed downward response. This will depend on the values of R and C in relationship to the delay time t. Let's consider some specific component values that will give us a small time constant. So we'll start off with R is equal to 1 k ohm and C is equal to 1 microfarad. When we multiply R and C together, we get the time constant will be 0.01 seconds. This small time constant shows in the circuit here with very little noticeable time change in the circuit response. We can look at a higher time constant by increasing the capacitance to 100 microfarads. Now the time constant will be equal to 1/10 of a second. At this time constant, we can easily see the decay at this time resolution. We can also consider a value of 0.01 farads that gives us a very high time constant of 10 seconds. When we look at this, we see that the droop is almost imperceptible, and we basically have a hold circuit.